Assalamu alaikum guys, this is our next topic, interpolation and Lagrange polynomial. One of the most well-known classes of the functions mapping the set of real numbers into itself is algebraic polynomials. You guys already know what are the polynomials, right? So this is a polynomial. What it does, it takes any x is a real number and Pnx gives you another real number. That's why they said function mapping the set of real numbers into itself. So any polynomial is a function from R to R. It takes the points from the real number and gives you the points from the real number back to you. Okay, and this is the nth degree polynomial because the highest power here is n, and an is not equal to 0 because if an is a 0, then the highest power is n minus 1, not xn. So the highest power should not have the 0 coefficients. All others can be 0. Okay, now this theorem Weierstrass, we call it Weierstrass approximation theorem. This says that if f is any function that is continuous on AB, then there exists a polynomial Px such that Fx and Px are very close to each other. It means for every function Fx can be approximated by a polynomial. This is what we mean basically. Epsilon is a small number. It means if I take the difference of f and p, the difference is very small. It means your fx can be approximated by this polynomial px. You remember in our last session, I said something about the Taylor's polynomials. So functions can be approximated by Taylor polynomial. And in this book, the Taylor polynomials are discussed in section 1.1. I did not go through chapter 1, but I did something in our last online session. So what was the Taylor polynomial? I can show you again. If fx is any function which is continuous and has derivatives, continuous derivatives up to order n, right? Then any fx can be written as f any point x naught plus f prime at x naught x minus x naught plus second derivative at x naught divided by 2 factorial and x minus x naught square. So we keep on increasing the power. You see there is no power of x here. There is 1 power of x, 2 power of x, and the same derivative is being multiplied. Next will be 3 divided by 3 factorial and so on. Okay, you can go to any derivative. So if you want to take n terms or degree n, if you want to take just n terms, so I will stop at one derivative before n minus 1 factorial x minus x naught to the power n minus 1, and you can stop here, but this is not equal, then it will be approximately. If I don't stop and continue till infinity, then this will be equal. So this is the Taylor polynomial. Okay, this is the Taylor series or Taylor polynomial. Up to here it is Taylor polynomial Pn minus 1x. Okay, but if I go to infinity, we call it Taylor series. Up till infinity, it's called series, Taylor series. Up to some power, if I stop here, it will become polynomial. And uh, if x naught is equal to 0, if x naught is 0, then this becomes f of 0 plus f prime 0 x, because x minus 0 is x, plus f double prime 0 divided by 2 factorial and x square plus so on up to f n minus 1 0 by n minus 1 factorial and x to the power n minus 1. This is the n minus 1 degree Maclaurin polynomial. You can also call it Taylor, but when x is 0, x naught is 0, we call it Maclaurin. Okay, Taylor polynomial about x is x naught equal x is equal to x naught. This is what we say. About x is equal to x naught. But if x naught is 0, we call it Maclaurin. When we call it Maclaurin, we don't have to say it's Maclaurin about 0 because it's automatically understood that it is already always about x equal to 0. So so here this is a function fx is equal to e to the power x, okay, and x naught is equal to 0. It means we are taking Maclaurin. Taylor polynomial about x naught equal to 0 means Maclaurin. So if you look at this Maclaurin polynomials, you can easily find out. This is the first term, first two terms, first three terms, first four terms, and so on. Okay, here we stopped at, so this is, if you want to see this, this is f of 0 plus f prime at 0 x. Okay, what is f of 0? F of 0 is 1, e to the power 0 is 1, so c 0. Its derivative is also ex. So if I take the value at 0, it's again 1. Okay, so that's why f0 is 1, f prime 0 is 1. Similarly, f0 is 1, f prime 0 is 1. And for the third term, because these two terms are the same, the third term is f double prime 0 x square by 2 factorial. So f double prime 0 is again 1 because the derivative of ex is again ex. At 0 it's 1, so you got x square by 2. So you can stop anywhere. This is the polynomial of degree 0, polynomial of degree 1, polynomial of degree 2, polynomial of degree 3, and so on. So we wrote here polynomial up to degree 5. And you can see how they are approximating. This blue curve is your original function ex, and you see this is p0. P0 is a very bad approximation. Our function is going there and this is going here, right? But when I take one term, it's little better. It's little better, you see. So now p5 is very close to ex, you see, on the right side. P5 on the left side, p5 is going down here. It's not very good, okay, but at least on the right side it is giving me a good approximation. Okay, so better approximations are defined are obtained for this function if the higher order Taylor polynomials are used. Like here we use P5, which is very close to the Taylor polynomial, but P0, P1 were not very good approximations, right? So what, this is not true for all functions. There are some functions whose approximations are very bad, even if I take higher order polynomials. So he gave this example. If we take fx equal to 1 over x and x not equal to 1, then the approximation is very bad. You see, what is the value of this function at 3? F of 3 is 1 over 3, right? If I put x equal to 3, it is 1 over 3. This is my fx. But if you find the derivative, if you find the Taylor polynomial, find the derivative is fx is x minus 1. So first derivative minus x square, second is x minus 3, and so on, right? So if you find the Taylor polynomials here, these are the Taylor polynomials up to any degree k, okay, up to any degree n, sorry, we are going till n. So for example, if I want to write phi 2x here, phi 2x means I have to start with 0 and go up till 2. So first will be minus 1 to the power 0 x minus 1 to the power 0 plus minus 1 to the power 1 x minus 1 to the power 1 plus minus 1 to the power 2 x minus 1 to the power 2, right? Up to 2 I have stop here. First I give k is equal to 0, then k is equal to 1, then k is equal to 2 here. Okay, so what is the polynomial? It becomes 1, right? And minus 1 x minus 1, so minus x minus 1, and this is plus x minus 1 square. This is your polynomial. You can open it up and see, simplify it, right? But if I want to find the value 3 from here, what it gives you, this is n is equal to 2, so we considered this. So he wrote many polynomials, like p01, p1x, p2x, p3x. This is the value of n. So if I want to find the value at 3, p2 at x3 should be equal to 3. Let's find it from here. p2 at 3. p2 at 3 is 1 minus 3 minus 1 is 2, and plus 3 minus 1, 2 square. So it becomes 1 minus 2 plus 4. So that gives you 3. 4 minus 2, 2 plus 1, 3. You see, this is the value. This is V3 at 3. And you see how bad is this approximation. Your f of 3 is 1 over 3. Your f3 is 1 over 3. And P3 is 3. See how bad they are? They are not even approximating each other, right? Even if I increase the number of terms, see, if I take P5 of x, P5 at 3 gives you minus 21, far from 1 over 3. So see, for this function, Taylor polynomials are not giving you a good approximation. Okay, but if you keep yourself closer to 1, you see, this is the Taylor polynomial about x is equal to 1, right? So if you keep yourself close to 1, then it will be a good approximation. For the points which are very very close to 1, it may give you a good approximation. Okay, but far from 1, Taylor polynomials usually do not give a good approximation for the function. So for that reason, we take the help from Lagrange polynomials. We call it Lagrange interpolating polynomials. Lagrange interpolating polynomial have a simple formula. Uh, this is the linear. Linear means order degree 1, right? Linear means the polynomial of degree 1. So first of all, I'm starting from Lagrange polynomial. And what do we mean by interpolation? Interpolation means we have to agree at some points. For example, if I have 2 points, one point is here, one point is here. So I want to find a polynomial that gives you exactly same value here at these 2 points. So we call polynomial interpolation. You see, interpolating means agreeing with the values of f. For example, your function was going through these two values. So at x naught, your function is fx naught, and at x1, your function is fx1. So what your Lagrange polynomial will do, it will exactly pass through these values, and the difference between them anywhere in between will be very very small. They will be closely approximating each other, but at these 2 points they will be exactly the same. Okay, so what we do is we define these two functions, L naught x and L1 x. L naught is the difference of x from x1 and x naught minus x1, and L1 is difference of x from x0. Okay, for 0 we use 1, for 1 we use 0. Okay, and now our Lagrange polynomial has this formula. After finding L naught and L1, just replace them here. L naught with the first value of the function, which is this one, and L1 with the second value of the function, which is this one. This is the Lagrange interpolating polynomial of degree 1. Now you put p at x0. You can see here, if I put x1, it will be 0. x1 minus x1 will be 0. And if I put x naught here, it will be 0. x naught minus x naught will become 0. So L0 is always 0 at x1, and L1 is always 0 at x naught. Opposite point. L0 is 0 at 1 and 1 is 0 at 0. But if you take the value at its own, 0 at 0 and 1 at 1, they will be 1. These are the properties of L0 and L1. Okay, that's how they made it. So if I want to find the value of p at x0, it is exactly equal to fx0, you see. And if I take the value of p at x1, it's exactly equal to fx1. Okay, so that's why we call it interpolating polynomials, that this polynomial exactly matches with the function at x0 and x1. Later on, we will see more points. We can take more points and interpolation. Maybe take a polynomial that passes through 3 points or 4 points or 5 points. We can do that as well. But we are starting from 2 points and linear polynomial. Linear polynomial is a straight line. Okay, linear polynomial is a straight line. So here it's an example. Determine the linear Lagrange interpolating polynomial that passes through 2, 4 and 5, 1. It means my x naught is 2, and f of x naught is 4, right? From this point. And here phi 1 means x1 is 5 and f of x1 is 1. Right? Because these are, oh, what's happening? Okay. So f of x1 is 1. Because if the point is phi 1, it means this is x and this is y. Y is the function of 1. Now we have to find L naught and L1. L naught is x minus x naught, x minus x1, right? We take the opposite. L naught 0 is x minus x1, x1 is 5, divided by x naught minus x1, which is 2 minus 5. And L1 x1 is x minus x naught, which is 2, this is x naught, and this is x1 minus x naught. This was x1 and x naught minus x1. Okay. So I got these two things. Now I will write them with fx. So this is my L0 and this is fx0, right? And this is L1x and this is fx1, right? So this is the formula. I wrote the formula and this is my Lagrange polynomial. Linear. It's a linear, so x has power 1. Any linear function has this form, ax plus b, right? So you got ax plus b. A is minus 1, b is 6. You can check the values, they are exactly the same. If you take p at 2, it should be 4. P at 2 should be 4. So you can see minus 2 plus 6 is 4. Right? And p at 5 should be 1. P at 5 should be 1. So minus 5 plus 6 is 1. So see, exactly interpolating these 2 points. So if you look at the graph, this is the graph of our polynomial. Okay. So we can generalize this concept to any number of points. Linear interpolation. We are still talking about linear interpolation to any number of points. So to generalize this linear interpolation, consider the construction of a polynomial of degree at most n that passes through n point n plus 1 points. Okay, because if you have 3 points, it is not possible to draw a straight line from 3 points, but we can draw some curve passing through 3 points. But when this is a curve, then your degree will be greater than 1, not equal to 1, right? So it will not be linear anymore. So we are generalizing the concept of linear interpolation from 2 points to a degree of order n from n plus 1 points. You see, when you had 2 points, your n was 1, 1 less. Now we have n plus 1 points, so my degree should be at most n, 1 less. Okay. So for that purpose, we will define L0, L1, L2 and so on. Okay. So because now there are many, the degree is not 1. Okay. And L0 and L1 are also more than 1. Now you don't only have L0 and L1, you will have more than that. Okay. Because there are n plus 1 points now. And similarly, your degree is not 1. So we have to mention the degree as well. So that's why they are using 2 subscripts, ln and k. Ln k comma k means n for the degree and k for the number of points, 0, 1, 2, 3, 4. Point 0, point 1, point 2 up to n points. Okay. So how to write this? What you will do to write this nk, I will take the difference of x from every point. X minus x naught, x minus x1, x up to x minus xn. But one of them will be missing. You see, there is no x minus xk. This is missing. You see, if you look, k minus 1 and k plus 1. So in between them, there should be x minus xk. But that is missing. That is the only thing. For k, x minus xk will be missing. Okay, and what happens, and now I will replace every x by xk in the denominator. It is the same thing, whatever you written in the top, that's how you remember it. Whatever you wrote at the top, now replace x by xk, replace x by xk, every other thing will remain the same. Okay, so now once you have written down these, let me write some of them on the board. You see here, if I want to write L21, It means there are 2 points, degree 2. So I will write, or let's say L3. We have 3. So I will start from x minus x naught, x minus x1, x minus x2, x minus x3. But this 1 should not be here. So it means it will be x minus x2 and x minus x3. This 3 will tell you where you have to stop. This 3 is this 3. Okay, you have to stop at 3. But this one says that there is no x minus x1 term. Okay, there is no x minus x1 term. This is missing. Okay, this is what you have to remember. Now we will divide by the same thing, but x replaced by which one is missing? X1 is missing. So I will replace x by x1. X1 minus x naught, x1 minus x2, and x1 minus x3. That's how we write L31. If you want to write L30, L30 will be x minus x1, because now x minus x0, this will be missing now. 1, 2, 3. Okay, and whichever is missing, that will be replaced here. So x will become x naught. X naught minus x1, x naught minus x2, x naught minus x3. Okay, and if you want to write, the last one, because for L3 I will have up to 3, right? So similarly you can write L032, L32, you can write L33. Okay, you can write L30, L31, L22, and L33. They can be written as similarly. So that's how you can write these L0, L1, and L2 for polynomial of degree more than 1. After getting that, we will keep multiplying these with x0 and x1 and so on. So you see our Taylor polynomial will become, we will take all these, keep multiplying with fx and add them. Okay, so this will give you the Lagrange polynomial of degree, any degree n. Okay, so this will be equal to, equal to, equal to, equal to. Okay, that's your Lagrange polynomial. So you take ln0, multiply with x0, then take ln1, multiply with fx1, so on up to n, lmn, multiply with f of x n. So here use the members called nodes x0, x1, x2. Now you see there are 3 points. These are called nodes as well, which are the points given to us. X0, 2, 2.75, and 4 to find the second Lagrange interpolating polynomial. Second means second degree. Okay. So if you want, you can call them just L21. Basically, this is L20, this is L21, and this is L22. But for simplicity, they wrote L0, L1, L2, because we already mentioned that n is 2, right? N is 2. So it means I need 3 of them, L0, L1, L2. But remember, because we are using 3 of them, so there will be 2 products at the top. For 0, x minus 0 will be missing, means x minus 2 will be missing. X1 and x2 will be there, right? And because this 2 was missing, so that's why x equal to 2 here, x equal to 2 here. So this becomes 2 by 3, and this, you see, these will be second degree. Reason is we are finding second degree polynomials, so they all will have second degree. Okay, so after finding L0, L1, L2, you see for L1, x minus x1 is missing. What was x1? This was 2 minus 7, 5. That is missing here. And here the last one is missing, x minus 4 is missing here, right? That's why you see 4 here. Whatever is missing, you see in the denominator. Now these points are also given to us, f of 2, f of x1, and f of x2. These all are given to us because the function is given. Function was 1 over x, so I calculated this. F of 2 is 1 over 2, right? F of 4 is 1 over 4, so you calculated all of them. And now we will just replace. So your polynomial, if you expand, it is fx naught L0x plus fx1 L1x plus fx2 L2x. Okay, so we put L naught x the value and fx, this is here and this is here. Okay, you see this was 2 over 5, right? 2 over 5, but f4 is 1 over 4. So if you multiply this 1 over 4, this will become 1 over 10. 2 2s are 4 and 5 2s are 10. That's why you saw 10 here. Okay, you see 10 here. Similarly, fx1 is 4 by 11. So 4 by 11 when gets multiplied by L1, you will get this. So this is your second degree, you see x square, second degree polynomial. And now if I approximate using this second degree polynomial, your f of 3 was 1 over 3. 1 over 3 is 0.3333, right? And now you see using this polynomial, if I find p of 3, that is 1 over 22 into 9, is it 9? And 35 by 188 into 3, so 3 into 35 is 105, plus 49 by 42 is 0.32955. You see how close it is to 0.33, right? You see Taylor was very bad. You see, Taylor approximation gives us a very bad approximation for this function. But see, Lagrange second degree polynomial gave us a very good approximation for this one. Okay, so here if you look at this was the graph of y is equal to f of x. This is your y is equal to 1 over x, right? Y is equal to 1 over x, and this is the v2x which we just calculated. This px, this is px we just calculated. So see, close to 3, close to 3, not just close to 3, in this whole interval. You see, in this whole interval, it's a very good approximation in this whole interval, not just near the point. Taylor theorems are good near this point. If you are very close to x3, Taylor polynomial is a better approximation. But if you want to see in a bigger interval, then Lagrange interpolynomial gives you a very good approximation. You see, even up to this, it's not a bad approximation. But if you go little far, then it started bad. But you see, close to 3, not just close, at 2, at 4, even they are giving us a very good approximation at all these, right? Okay. So this is the Taylor Lagrange interpolating polynomials. I hope you understand this. So try to understand how to write this lnk. With a little practice, you can easily write lnk. Okay, you have to start with x minus x naught, so on up to x minus xn, because this is n. But only one term will be missing, which is k term. If it is x minus 2, then x minus 2 term will not be there. Okay, if it is 0, then this first term will not be there, and you will start with x minus x1. And in the denominator, same term, only x replaced by this number, x replaced by x naught, this x replaced by x naught. Okay, so that's how you can write these polynomials. Do little practice with writing this. Do a little practice with writing this expression, and then Lagrange polynomial is very straightforward. Why? Because you just have to multiply fxk with ln kx and take the sum on all k from 0 to n. Okay, so that is your Lagrange interpolating. I hope you understand this concept. So try to do this, and this is the section 3.1 in your book, third chapter, first section. Just pick any question from the exercises, pick some exercise and try to do it, or write anything on your own. Just write any function and try to find second degree or third degree polynomial, but it's better if you pick something from the exercise. All right guys, so see you with the next topic. Till then, bye from me. Wassalam.